initial stage of 0.8
So
meter
we will
cube per
stop here.
kg.
Again,
This one is
before
meter
we
cube
stop,
per kg.
before I
It
let you
means
go
that
off,
this is a
any other
specific
comments or
volume.
questions?
Okay, and 25
So
degrees Celsius to a final
if not,
stage of 0.1 meter cube per kg and
I think we'll stop here.
287 degrees Celsius. Determine the
Then
reversible work
Melvin
input
and
and
partner, please
increase
don't
in
forget
exergy of the
your
oxygen during this
reports.
process.
Okay.
Assume that the surrounding to
So we
be at
stop here.
35
You can go
degrees
off and see you
Celsius
back on Friday
and
morning.
100
Bye bye.
kilopascal. Given that the oxygen is ideal gas with a constant specific heat R and Cv. So first, you need to write down the equation for the closed system. Okay, exergy of the closed system, because the question asks for the reversible work. Okay, so reversible work should be equivalent to the exergy change from state 1, to state 2. Okay, and then you also have to measure the increase in exergy. So same thing, phi1 minus phi2. Compare the exergy between 1 and 2. So for this case, what we have, we need to find the exergy change. So first is a change of the internal energy. Remember that all terms are here. So we have change of internal energy. Then secondly, work done to the surrounding. Third is the irreversibility. Fourth, kinetic energy. And fifth is the potential energy. So we start from number 1. This is 1 to 2. You can see that phi1 minus phi2. So U1 minus U2. Change of internal energy. Secondly, work done to the surrounding. So you have to, the system have to work against the surrounding pressure. So P0. This is the surrounding pressure. And then change of the volume. Volume is V1 minus V2. Okay, and then next one, negative. This is the losses, which refer to the irreversibility. And reversibility also refer to the temperature of the surrounding multiplied with the change of the entropy. Okay, and then plus the change of kinetic energy and the change of the potential energy. These are terms that we have. So I don't see any value for potential energy and kinetic energy. So I will assume that there's no change between the initial and final stage for kinetic energy and potential energy. So I need to measure these 3 terms. Okay, so you can go back to this. Okay, maybe I convert the video. You can go back to your lecture note and then get the equation for this ideal gas. Remember that you only can use this for the ideal gas, which is the oxygen, air, or whatever gas that's stated as an ideal gas. Right? Our syllabus will cover only steam or ideal gas, not other gas you consider. Okay, so let's from here, you can use the equation for the ideal gas over here, ideal gas law. Okay, so you want to get the delta U. Okay, and then you want to get the delta S. So we start from delta U. Delta U refer to the change of the internal energy. Okay. Okay, so maybe we do it one by one. U1 minus U2. So will be equal to CV delta T. So CV is given 0.690 and delta T should be T1 minus T2. So T1 is 25 degrees Celsius, T2 is 287 degrees Celsius. Don't state that must be bigger minus smaller. You have to follow this. If I put 1/2, you must always use 1/2. Later I will explain in detail what's meaning here. Okay, so this is exergy of the state 1, exergy of the state 2. Okay, so which one is higher? If the system deliver the work, phi1 will be higher than phi2 if the system deliver work. Okay, because the exergy has been used to deliver work. So the exergy left over at the second stage should be lower. But if if the work done is to the system, there's a two case, work done to the surrounding. Okay, the system do some work to the surrounding, or it do some work for other system output work. Then the phi one will be higher than phi two because some of the exergy has been used. But for some of the system is actually some work is transferred to the system, work done toward the system. So the system supposedly the phi two will be higher than phi one because it absorbs the work done from other. Okay, so it doesn't matter. It's also considered as a work done, but just a work done to the system or work done from the system. Okay, it's input and output, but there should be the same value, just negative and positive value. Okay, so now delta t, we just use 1 or 2 for all of them. So 1 is 25 and 2 is 7. Of course, if just a delta t, you do not want to convert to Kelvin also can because it will have the same value. But when you have the division or multiplication, make sure that you convert to Kelvin. But I think to make it consistent, we always convert to Kelvin. Okay, so 25 plus 273. Okay, so we have 298 Kelvin minus this one 2x7 plus 273. So 560 Kelvin. So I get negative 180.75 kilojoule per kg. So if I refer to the change of internal energy, sorry, I refer to U1 minus U2. So it have the negative 180. So it means that U2 have the higher energy than U1. Okay, so that the system is actually absorbing the energy from somewhere, okay, from outside the system. Then we look on the second term, V0, V1 minus V2. V0, V1 minus V2. For this case, same thing. V0 is the surrounding pressure, 100 kilopascal. But remember, just put 100 because the final answer is in kilojoule per kg. Okay, and then V1, remember the final answer is in kilojoule per kg. So that this volume should be in terms of the specific volume as well. Okay, so here we have V1 0.8, V2 0.1. So here you get the positive value of 70 kilojoule per kg. Remember to always check the unit. You can see that this, what's the unit for P0? P0 is a kilopascal, or I can put kilo Newton over meter square. Okay, and then what's the unit for V, volume? So here we have the specific volume of meter cube per kg. So you have the meter cube per kg. Okay, so I cancel, I get the kilonewton times meter over kg. So Newton times meter is a force times distance. Okay, Newton is a unit for force and meter is a unit for distance. So force times Newton, you get kilojoule over kg. So our unit is valid. Remember that all the terms must have the same unit. Okay, so that's why here I put 100 instead of 100,000. Okay, so the third terms is the ds t0 s1 minus s2. So that you can see that not every term will have the same work done. Some of them, same direction of the work done. Some of them can be a positive, some of them can be a negative. Okay, so for this case, you can see that change of internal energy, okay, negative, but work done to the surrounding, positive. Then we look on the third one, irreversibility. T0, S1 minus S2. So T0 here is the surrounding temperature, which is 25 degrees Celsius. So 25 plus 273, you will get 298. Okay. So S1 minus S2. S1 minus S2, you can use any of this equation. Okay. So which one you want to use is up to you lah. But according to this question, we are given R and CV. R and CV. Okay, maybe I can use the second one. Okay, delta S equal to CV, non-whatever. Ln. This one is a 1, 2, so this one same thing. 1, 2 plus R ln V1, V2. Okay. My 8. Okay, lah, you calculate that. CV is 0.69 ln D1, D2. D1 over D2. D1, D2. D1, 25, D2, 278. I remember to convert to Kelvin. So I get negative 0.6308. And then R 0.2598 ln V1, V2. Let me know if I move too fast that you can follow. Okay, 1.2. Okay, let's see you can get the same answer or not. So I have the change of internal energy, work done to the surrounding, and is irreversibility. And now I can combine all together. So reversible work equal to negative 180.78 plus 70 minus 31.2. So I get negative 141.98. And this negative 141.98 kilojoule per kg is referred to the phi 1 minus phi 2. Okay, so it means that phi 2 exergy at the state 2 is higher than exergy of the state 1. So that I would say that reversible work is 141.98 kilojoule per kg. Remember that work done should be the positive value, just the work done to the system or work done from the system. And this is the work done to the system. Okay, the system is absorbing the exergy from external force. Okay, and this is also referred to the increase in the exergy. Okay, can you follow? So that actually you want to put phi 1 reversible work. Reversible work here is phi 1 minus phi 2 or phi 2 minus phi 1, doesn't matter. Okay, because we at the beginning we may do not know the system is actually deliver work or the system is absorbing the work. Okay, especially when, okay, for this case quite clear. Okay, you can see that volume is increasing, sorry, is decreasing. So it means that compress it. So you will have more energy. Same thing for the temperature, is increase in temperature. So it absorbs the energy. This is very clear. But some of the case that volume increasing. So it's increasing, it means that it's expanding. Expanding means that it's releasing the energy, but the temperature is increasing. So that case you will have a one positive and one negative. So make you not really know that which one is actually contribute the most. Okay, so reversible work, we always simply put phi 1 minus phi 2 or phi 2 minus phi 1. Okay, so if phi 2 is bigger than phi 1, it means that the system is absorbing work, absorbing energy. If phi 2 higher than phi 1, okay, sorry. If phi 1 higher than phi 2, it means that the system is delivering job, delivering work. If phi 2 higher than phi 1, it means that it is absorbing. Okay, it's a work done or something like that. One is a heat pump, one is a heat engine. Okay, any question on this? Can I follow? Okay, good. Okay, then we move to the next question. Okay, after this example, I think we can continue with the past year question. Okay, maybe you can complete this in 1 hour. Okay, this example 2.6. Okay, steam. Steam is not the ideal gas. So that for this case, we are not able to use the ideal gas law anymore, but we have to refer to the steam table. Okay, in the exam, because we have the we have the online exam, so you have to prepare your own steam table. So it can be a soft copy or can be a hard copy. And the steam table that we use is normally this version. Okay, from Roger. And title called Thermodynamic and Transport Properties of Fluid. It's not called steam table alone because it's including many types of the fluid, which is a non-linear fluid, okay, which do not obey the ideal gas law. You can see that from here, other than steam, we still have the mercury, ammonia, this CF2, this one is a refrigerant, refrigerant 134A, which is used in the cooling system. Okay, but that's we not really cover, we just cover the steam. So from here you can see that what we have the saturated water and steam, superheated steam, supercritical steam, okay, and compressed water. So let's look on starting from this saturated water and steam. Okay, what information you can get from here? Saturated water and steam. Okay, so from here you can see that at every we look on the first three columns, temperature, pressure, and volume. If you don't know what is DPS, you look on the unit, degree Celsius, bar, and meter cube per kg. Okay, so we look on temperature. This saturated water steam will tell you what is the saturated pressure of the steam at the certain temperature. For example, this one. Let's say the temperature of the surrounding is 25 degrees Celsius. Okay, so the steam will reach the saturation pressure at 0.03166. Okay, it means that when the temperature when the pressure lower than this value, you will have the superheated steam. Okay, before Below this value, you will have the mixed with the mixture of the steam and the water. Okay, at this value is a completely saturated. Okay, this is a threshold value. And then you look on this VG. VG is the specific volume. Okay, and then you look on the HF, second column, HF and HG. This is referred to the enthalpy. Enthalpy refer to the flow energy plus the change of internal energy. Flow energy plus internal energy. Okay, and you have the HF and HG. HF refer to the fluid, and HG refer to the gases. Okay, so if you want to use this table, then you have to check whether your enthalpy is in terms of fluid or gases. Okay, so you need to know that water is remain at the liquid form or in the gases form, or maybe in a mixture of them. You want to get the mixture of them, you also can do that. Okay, so in the middle there is a HFG. It's between these two. Okay, but we seldom use this slide. Later I'll teach you how to use this. Okay, and then same thing for S. S is entropy, which is the irreversibility or maybe disorderly. So you can see that entropy for fluid, entropy for gases, and SFG, the relationship between these two. Okay, if you check this, you can see that actually this FG is referred to the SG minus the SF. Okay, 9.128 minus 0.015, you get 9.113. Okay, the difference between these two. Okay, then this is the first part. And let's say that you have the pressure, but you want to know the saturated temperature. Okay, then you go to the second part of this saturation, water and steam table. Okay, you can see this one starts temperature, and we can go to find this one that starts with the pressure. Okay, so at a given pressure, it will tell you that what is the saturated temperature of the water or steam. Okay, what does this mean? Maybe we refer to the 1 atmospheric pressure. Okay, then we can see clearly. So 1 atmospheric pressure is here. Okay, you can see that at 1 atmospheric pressure, the saturated temperature of the water is 99.6. So above this temperature, the water will become the steam. Okay, so if more than 99.6, it means that you have to refer to the saturated, you have to refer to the superheated steam table. Okay, so this table will tell you what is the saturation level. Saturation level is mean the maximum possible value. Okay, at 1 atmospheric pressure or 1 bar, maximum temperature of water will be 99.6. More than this, it will convert to steam. This is the meaning. Okay, and then same thing, you can get the change of internal energy, enthalpy, and also this one entropy. Internal energy, enthalpy, and entropy. Okay, it means that these two table between starting from T temperature and starting from P pressure is actually the same. Just they arranged in different way. If you want to find the same value, okay, definitely fine. Let's say I want to find let's say you can see at 0.015 pressure, the saturation temperature is 13. Same thing, you go to find 13 over here, the saturation temperature will give you 0.015. Okay, so it's actually comparable. So you can use any of them, depends on what you like. Okay, or normally it depends on you have temperature value or you have the pressure value. And then next is about the superheated. Most of the case when we use the steam to run the steam turbine, is referred to the superheated steam. So actually it's more useful for superheated. Okay, so for superheated, you can see that first we have the pressure, and it will tell you what is the saturated temperature. Okay, in the bracket is saturated temperature, and at different temperature you will have the different. Okay, you have the different V, specific volume, U, internal energy, H, enthalpy, and S is an entropy. Okay. So refer to this, you can get all information from here. Okay, now go and download this Steam table. I shared this before in the Google Classroom. Maybe I try to share again. I attach again. Very difficult to scroll down and find it. So you go and download it and then we do it together. Or you can also get it from internet. So this Steam table. Okay, you download it. Just posted. You can check. And then we come back to our example. Maybe give you 1 minute to get it. Okay, so Steam. So Steam, when you see Steam, is not idle gas anymore. And then enter an adiabatic turbine. Adiabatic here refer to no heat transfer across the turbine wall. Okay, so we can consider it as an isolated system. No heat loss. And at 6 megapascal, 600 degrees Celsius and 80 meter per second. Now we can see that you have the velocity. So whenever you have the velocity, it means that you have the kinetic energy. And this turbine is keep rotating, continuous system. So we have the flow system now. Okay, and live at 50 kilopascal, and this will be the second stage. The surrounding of the turbine are at 25 degrees Celsius. And if the power output of the turbine is 5 megawatt, this is actual power. Determine the power potential. Okay, is don't want the unit in kilojoule per kg, but you want the unit in the megawatt. Okay, so firstly, we write down the potential of the steam. So potential of the steam refer to the exergy of the steam at the inlet condition. So at the inlet condition, that is mean that we have to take care of the inlet and we compare with the environment. Okay, this is only the maximum potential energy of the steam. Okay, so based on this, so first I need to find what? The first term, remember, change of the enthalpy. Okay, and then we do not have any work done. Okay, we write down change of enthalpy, H1 minus H0. Secondly, we have the work done to the surrounding, but for this flow system, it is definitely negligible. So the next term, we have the irreversibility. Also same thing, S1, S0. And then third, we have the change of kinetic energy. Okay, so kinetic energy, we have the V squared over 2. And then potential energy, Gz. So this term, 0, because they do not give any information about the potential energy. Okay, next, we have to find H1 and H0. Okay, maybe you can separate this into 3 parts. State 0. Okay, so state 1, we have this pressure, 6 megapascal, temperature, 600 degrees Celsius, velocity, 80 meters per second. You just write down all the information you have. And this and then surrounding, we have the pressure. It's not surrounding, if not stated, normally the pressure may not be stated because we know that surrounding pressure is always 100 kilopascal or 1 bar. It will give you the temperature only. Your temperature can be different from different location. And then velocity, if not given, it means that 0. Okay. So now we want to find what H and S before you can get the exergy. So here you have H and S, and I can call it at 1, phase part 1. Same thing, phase 2, S2, H0, S0, 0. This is 2, 2, 2. Okay, now we start from first part. Maybe you try to find before I got you. Maybe you can get the H1 and S1 from the steam table. You try first and share your answer in the chat box. Okay, so let's do it together. We go to steam table. Okay, and now we want to know that this condition is it steam or water. Okay, so I go to the steam table. I go to the saturated water table, and maybe I myself is preferable to use the temperature lah. So temperature at 600 degrees Celsius. 600 degrees Celsius. It's not here. So definitely it will be superheated. Okay. So it means that now we have to, we still have okay, then we refer to the pressure because the temperature up to 100 only, 100 degrees Celsius only. So we refer to the pressure. The pressure we have is a 6 megapascal. 6 megapascal. And then from here, this is bar. So 6 megapascal convert to bar is 60 bar. Okay, we go to the 60 bar. 60 bar. Okay, and then the saturated temperature will be 275.6. So beyond this value, the water will become steam. Okay, because at higher pressure, of course, the boiling point of the water will be higher. So at this point, if the temperature more than 275, then it will become the steam. So we check on this. The temperature 600 degrees Celsius. So it's very far from the saturated. So it will become the superheated steam. So same thing, at the superheated steam, I find the 60 bar. Okay, at the pressure state, 60 bar. Okay, so this is the 60 bar. Okay, and then we want to find the specific volume, H and S. Specific volume, I think maybe we don't need, okay, for this case. So we find H and S. So for this case, the temperature of 600 degrees Celsius. So we refer to the top, I can see that the temperature 200, 250, 300, and go to 600. And when we drag down, yeah. So this is what we're looking for. Okay. So our H is 3657 and S is 7.166. And S 7.166. Okay, the unit is different. One is a kilojoule per kg for enthalpy, and for entropy will be kilojoule per kg Kelvin. Okay, then we go to the stage 2, do the same thing, 50 kilopascal and 100 degrees Celsius. So I go to the saturated pressure. 50 kilopascal. 50 kilopascal refer to 0.5 bar. 0.5 bar. So over here. So the saturated temperature is 81.3. So beyond this value, it will be the superheated steam. Okay, so we go to the superheated steam table and find 0.5. Okay, somewhere here. Okay, 50 kilopascal. So it's at 0.5. So 100 degrees Celsius. 100 degrees Celsius is over here. Okay, so we get the H2683 and S 7.694. Okay, then go to the state 0. State 0 is a bit special. You can see for most of the case, state 1 and state 2, when the steam go into the turbine and come out from the turbine, it should be in superheated steam. Okay, because if this not in the superheated steam, this will destroy the turbine. Why this is? Okay, when the steam go into the turbine, it's in the steam, in the gaseous form. Okay, if in case of the steam is not superheated steam, when it come out, some part of the steam will be condensed, become water. And as we know that water have much higher density than the steam. Okay, so this will cause damage to the turbine because you will experience unbalanced force. Some of them is a liquid, some of them is a gases. Okay, so for the design of the steam turbine, we have to make sure that when the steam go into the turbine and come out from the turbine, both must be superheated steam. Okay, so for state 1 and state 2, we know there's definitely steam, most of the case lah, unless a special case that maybe the design is not too good or just want that's your understanding, then it have possibility that it come out is not the superheated steam. Okay, but the final stage is the environment temperature. I think I don't need to tell you what is the condition. You already can tell me either atmospheric pressure and temperature of 25 degrees Celsius. The water will remain as water, correct? So what we need to do for this case? So you need to get the composition and the enthalpy and entropy for this water. Okay, simply we refer to the steam table, and you can maybe try future properties of water. Okay, okay, here don't have. Okay, from these future properties of water, we can get the VF, the volume, specific volume of steam if needed lah. And then we want to get the enthalpy and entropy. We have to go back to the saturated water. And we go to the temperature of 25 degrees Celsius. Okay, temperature of 25 degrees Celsius. And then we can get the HF here, 104.8. Of course, what we are looking for HF, 104.8. So I write down 104.8 kilojoule per kg. Okay, we refer to temperature of 25 degrees Celsius. So it means that at 25 degrees Celsius, the HF will be 104.8. Okay, and then next, 0, enthalpy 0.367. Okay, and remember to write your unit. Remember, do not use the pressure table for this case because you do not know what. Okay, you want to use the pressure, then you have to refer to the one. Let me check if you can use this. Okay, you don't come to this pressure of 1 bar. You have to use the temperature as a reference. because at 25 degrees Celsius, our water is incompressible. Okay, so we have to refer to the value for the temperature table over here. Okay. Okay, can you get it? So we get this H1 S1, H2 S2, and H0 S0. Then I think I should able to get the psi1 minus psi0. I just substitute inside psi1 minus psi0. H1, what's the value here? 3657 minus 104.8. D0, temperature of the surrounding, 25 degrees Celsius. So plus 273, 298. S1, 7.166. S0, and then V square. So this one, actually you have to measure the change of the kinetic energy. Okay, so I would say that this V2 square will be initial tap velocity, 80 meter per second. 80 meter per second minus 0 square over 2000. Okay, because I want the unit in terms of kilojoule. So I divide by another 1000. So I get the value here. So I get 1529.3 kilojoule per kg. But haven't complete now. You can see that the question asks for the power potential of the steam at inlet condition in megawatt. So how I convert from kilojoule per kg to megawatt? So it means that I need to multiply with the mass flow rate. Okay, then only can get the megawatt. So it means that I need to get the exergy, which is equivalent to the mass flow rate, multiply mu1 minus mu0. Sorry, psi1 minus psi0. But how to get the mass flow rate? The mass flow rate, normally you can get it from the actual power output. Okay? So from this question, the actual power output given is 5 megawatt. So you can use this as a reference. Okay. So I would say that power output, sorry, maybe I call actual power output. Actual power output equal to the reversible power output minus the losses. Okay, and the losses here I can call it as a irreversibility. Okay, which refer to the T0 S2 minus S1. Okay, so for this case, then sorry, let me add more page. Okay, so that now I want to remove this T0 S2 minus S1. Then I can get it from this B reversible. Okay, so you have work done to the surrounding. So we have the H2 minus H1. Okay, and then plus second term is negative D0 S2 minus S1. Okay, and then next term is the change of the kinetic energy. So V2 square minus V1 square, you are 2000. This is referred to the reversible power. And we want to minus the irreversibility. So for this case, you want to take out this. Okay, so I remove this term. Okay, this is the losses that I add back into the system to give it to measure the potential of the energy. But now I don't want the potential energy, but I just want to the actual energy. So the P actual now will be equal to the H2 minus H1 plus V2 square minus V1 square over 2000, and then multiply with the mass flow rate of the system. Okay, so from here, I know the actual power is 5 megawatt. So I put 5,000 kilowatt because everything in kilo. Okay, then I write in the value that I have, H2 minus H1. H2 is 2683 minus H1 3657 plus V2 V2 80 and 140. Okay, and then we get the mass flow rate. Okay, but please take note that this term may give you the negative value or positive value, but it doesn't matter. The mass flow rate must be the positive. Okay, the only difference is, as I said, work done to the surrounding. Okay, work done to the system or the system supplying work. Okay, so that we can put the modulus over here, and we can continue to get the mass flow rate. So I have a 5,000 kilowatt mass flow rate. So I get 5.168 kilogram per second. Is that clear? So you can see that we can get the actual power based, we can get the mass flow rate based on the actual power. Just remove the irreversibility because the irreversibility terms will never contribute to the actual power output. But when you calculate the reversible power, you have to always consider the irreversibility. Okay, it means that you are actually adding back the value of irreversibility to calculate the maximum possible value, because you may able to reduce the irreversibility of the system. That's why you always have to consider that as your potential. Okay. So based on this mass flow rate and also this change of potential of this exergy, then we can get the potential of this steam in terms of megawatt, which is 5.16 minus 1529.3 kilojoule per kg. So I get 7.9 megawatt. Okay. So I solved the first one, the power potential of the steam at its inlet condition in megawatt. So it has a potential of 7.9 megawatt. Okay. Any problem to get this, to understand this? I think the difficult part is to get the mass flow rate. Remember that the mass flow rate always can be calculated from the actual power output by just removing the irreversibility or any other losses from the system. Then you will know that the exergy change, which part of the exergy change will actually contribute to the power output. Okay, but for this system, there is no other losses other than irreversibility. Okay, for some of the cases, they will tell you that there is a heat loss to the surrounding. Then you have to consider that as a losses minus that, and then you only can get the mass flow rate. Okay. Okay. Second. Okay. So first we get 7.9 megawatt. So second, reversible output. So first and second, what's the difference? You can see that the first we ask for the potential of the steam as an inlet. So this one we don't care about where is the outlet, when is the final stage. So it means that we take the phi 1 minus phi 0. But for second case, they ask for reversible power. So this one is in a process. So in the process, you should check the change of the exergy. So phi 1 minus phi 2. Okay. So again, we do the same thing, but now we find the phi 1 over phi 2. So B, I want to find the reversible power. So reversible power should be mass flow rate multiply phi 1 minus phi 2. And you can put a modulus over here just to check is a work done to the system or work done from the system. Okay, and same thing, mass flow rate. And this one I have the H1 minus H2 minus D0 S1 minus S2, and then we have also the this velocity, kinetic energy. Okay, so mass flow rate 5.168, H1 and H2 3657. S1 minus S2, S1. V2, V1 minus V2. So V1 is 80 and 140. Okay, so we get the reversible power 5.81 megawatt. Okay, so we come back to this question. Okay, so from this you can see that you have three different output. Okay, 5 megawatt, 7.9 megawatt, and 5.81 megawatt. So 5.81 is the maximum possible value from state 1 to state 2. Okay, and then 7.9 megawatt is come from the potential of the steam from state 1 to state 0, where we do not know when you want to stop. Okay, so 7.9 megawatt refer to the exergy for the entire system, sorry, for the inlet steam. Okay, but B is just refer to the exergy change between the 1 and 2. Okay, or maximum possible output between this process. And then 5 megawatt refer to the actual power output. So to get the second law of efficiency, remember is what we get divided by what maximum possible we get. So it's P actual, what we get, over maximum possible what we get for this process is P reversible. Okay, so 5 megawatt divided by 5.81 megawatt, then you will get the second law of efficiency, which is about 86%. Okay, can follow? This is a exam standard lah. So if you can answer this, normally no problem for your exam for this exercise part. No issue, seems like very good. Okay, then maybe move to the next one. But maybe we take a short break lah, for 5-minute break, and then we continue with the example 2.7. Okay, see you at 12:05. Yes, architecture, yes, correct. We divide by 2000 because we want to convert from joule to kilojoule. Previously, it's a 1/2 MV squared. Okay, so now become 1/2000. Okay, Jingwei, this is the calculation part is not included in the EE syllabus. So for EE student, you have to cover up to the concept of the exergy because you know the potential of the energy as well. So you know what's the that state and what's mean by exergy. Okay, and then what's the condition for this maximum possible output, something like this thing going on. Then this calculation may able help you to maybe better understanding in the concept of the potential of energy. Okay, but it's not much important compared to RME and RMH. Okay, Jingwei. So EE, if you don't understand the calculation in detail, it's still okay. Yes, Jingwei, you no need to prepare the steam table for your exam, but just need to understand the concept of exergy. Yeah. Mm. But of course, if you practice the calculation, I think will help a lot in your understanding of exergy. Okay, let's continue. 2.7. Okay, a piston cylinder device. Okay, we see the piston cylinder. We know that this is a closed system. Contain 0.05 kg of steam and at 1 megapascal and 300 degrees Celsius. Steam is now extended to final state of 200 kilopascal and 150 degrees Celsius doing work. Heat loss from the system to the surrounding are SDR. You can see that this question have the heat loss, which to the surrounding of 2 kilojoules. And assuming that the surrounding to be at 25 degrees Celsius and temperature of 100 kilopascal. So you need to determine the exergy of the steam at the inlet, initial, and the final stage. So same thing, write down the information that you need. So we need to do for initial state, final state, and the test state. Okay, so initial state, state 1. What I have, pressure, 1 megapascal, temperature, 300 degrees Celsius. Then what else? What else you need? Do you need enthalpy? No need because it's a closed system, but I need the internal energy. Okay, I don't know yet. And I also need the entropy. And another one is the specific volume because I need to calculate the work done to the surrounding. Okay. Then state 2, same thing. Okay, I think before we start, we have to find this information. Okay, and other information for this question. Heat loss, 2 kilojoule. The rest are, I think, okay. Mass, 0.05 kg. Okay, so first you need to find all the information from steam table. I think state 1 and state 2 relatively easier lah. You can find it first. But state 0, then maybe we can do it together. I can use it. Okay, continue lah. Using another steam table. If you want to directly jump to the superheated steam table for state 1 and state 2, fine, no problem. As long as you can get the value, it means that it's superheated. Okay, at the given temperature and pressure, you can get the value, it means that the fan is superheated. Okay, for example, maybe for this one megapascal and 300 degrees Celsius. I do not want to check on the saturated water table. I directly jump to here. 1 megapascal is 10 bar and 10 bar. Okay, 10 bar is over here. Okay, so you can see that the first temperature range is from 200. Below 200 is mean that it's not superheated. Okay, so for this case, we have the temperature of 150, 300. Okay, so our 300 is over here. So you get the value from here lah. Okay, then let's move to the stage 0. U, internal energy, entropy, and this. So we go to saturated table. We find for 25 degrees Celsius. Okay, so 25 degrees Celsius, we have the S for fluid 0.367. But U is not available over here. Okay, but for water, because it's non-compressed, not compressible, so the U and H will have a similar value or exactly the same value of 104.8. Okay, if you do not want to get a H value, you can refer to the temperature table and you find 25 degrees Celsius. It should be around here. Okay, between 24.1 and 26.7. Okay, and then you want UF, you do the interpolation between 101 to 112. Do the interpolation and get the U value, and it will be actually the same as what we get from the H table, from here, 104.8. Okay, so to make it easier, H and U will be the same value for non-compressible water. So we have our 104.8 as well. And now the volume, specific volume of water. So this one we can refer to the future properties of the steam. Okay, come here. And our temperature is 25 degrees Celsius. You can see that VF, volume for fluid, specific volume of fluid, 0.1003 times 10 power of negative 2. Okay, 0.1003. So should be times 10 power negative 3 should be 0.001003. Okay, actually it's a volume for water lah, if you see that. Okay, you divide by 1, sorry, 1 divided by this, actually, because this is in terms of meter cube per kg. If you want to get the density, it's just 1 divided by this value, you will get similar, almost close to 1000, 1003. Okay, so now I have all the information. I need to start to answer the question. First, the exergy of the steam at the initial and final stage. So exergy of the steam at the inlet should be X1. Okay, X1 will equivalent to M1. This is closed system, phi 1 minus phi 0. Okay, so M1, not 1, M is only have 1, no need to put 1. This M. Okay, so the first term for non-flow is a change of internal energy. Then work done to the surrounding. Then irreversibility, kinetic energy and potential energy. I think I can just skip lah because not here. Okay. Okay, you can put in all the value M 0.05. Okay, this is the exergy of the steam at the initial state. So I get X1. So the final state will be X2. Okay, now I want to find the final stage. I want to find X2. How much exergy left in the final stage? So same thing. I want to find the exergy of the final stage. I take the phi 2 minus phi 0. So it will become M U2 minus U0. U2 minus U0. U2 minus U0. V2 minus V0 S2 minus S0. Okay, so exergy of the steam at the inlet, I get 35.07 joule, kilojoule, sorry. And then X2, just compare the answer. I don't know if I'm correct or not. I just press calculator. Then 5.45. Okay. Then for the second part, the exergy change of the steam. So exergy change of the steam. So from X2 to X1, you have 25.45 minus 35.07. Exergy change must be take the final minus initial. Yeah, it can be positive, can be negative because they ask for the change only. So the exergy change will be negative 9.62 kilojoule. Very fast, you can answer the question. And then third one, exergy destroyed. Oh, yeah. Okay, exergy destroyed, normally we refer to the irreversibility, okay, and any other losses. So for this case, we have the irreversibility. We also have a heat loss of 2 kilojoule. So we have to combine the total loss over here. Okay, so we find the irreversibility. Okay, this is the irreversibility, and then plus the heat loss of 2 kilojoule. I put the modulus because the losses should be the negative value, sorry, it should be the positive value as well over here, and then both of them can be combined. Because some of the case you will use 2 minus 1, some of the case you will use 1 minus 2. Depends that this is a heat pump or heat engine. But for most of the question, we want to tell you in detail. So that we put the modulus, it never wrong. We're definitely correct. Okay? Exergy destroyed should be in positive. I mean that this irreversibility and heat transfer should not cancel out each other. Okay? That's why I put modulus so that you will confuse. So here I have 298 x1 S2 7.28 and plus 2 kilojoule. Okay. Okay, and then the unit here, you can see that if I get the irreversibility, the unit here will be in terms of kilojoule per kg, but the heat loss will be in kilojoule. So that you want to make it the same unit. So I multiply mass in front. Okay, so that it will become the same unit, kilojoule. So you have a total of 4.32 kilojoule of the exergy destroyed. And the last part, second law of efficiency. So again, we're doing the same thing. Second law of efficiency, P, what? P actual minus P reversible. So P actual, I don't know. But I know that X-ray destroyed is 4.32. But XG change is 9.62. So I can get 9.62, which is the total XG of the process, total XG change of the process. So this will refer to the reversible power minus the total losses, 4.32, divided by the reversible power, 9.62. Okay, you notice that here the XG change is 9.62 negative. But when we get the power of output, it should be positive value. Okay, just I say that the exergy lost to the, you can see that exergy x2 minus x1 is negative values, mean that they use the exergy to do work. Okay, so here is a work output. So I can get the efficiency, second law, 55.09. You can put in the percentage, 55.09% or 0.5509. Okay, any issue? Can follow on, then move to the next one. 2.8. Steam enter a turbine. Turbine is mean that flow. Steadily at 3 megapascal and 450 degrees Celsius, and the rate of 8 meter per second, 8 kg per second. So you are initial state, final state, and the steam is losing heat to the surrounding air as 100 kilopascal, 35 degrees Celsius at rate of 300 Kelvin, 300 kilowatt. And the kinetic and potential energy of this is change. Here are negligible. Determine the exergy of the steam at inlet. So again, I need to draw out the information that I have. State one. This is the first step you need to do most of the time. Okay, pressure. Then this is the flow, so I need the entropy and the enthalpy and entropy. And then we have mass flow rate, 8 kg per second, and the heat loss. 300 kilowatt. You can see that actually the question can give you in terms of power or energy. It can be in terms of kilojoule or can be in terms of watt. But actually the same lah, the meaning. Okay. Okay, then complete this table. 3 megapascal. 30 bar. So the first part, they ask for the exergy of the steam at the inlet condition. Okay, exergy of the steam at the inlet condition. So you need to find x1. And x1 equal to m phi1 minus phi0, which is equivalent to, then second is the work done to surrounding don't have the irreversibility. Then kinetic change of kinetic energy and change of potential energy. So I think we only have two terms. Okay. So the exergy of the steam at the inlet is 9,998.97.04 kilowatt. And second part, the maximum possible power output. The maximum possible output should be different from x1 because you have to consider the final stage. Okay, x1 is just the potential. You don't need to consider the final stage. But this one, you have to consider final stage. It means that you need to find x1 minus x2. Okay, maximum possible output. Again, I put the modulus because I do not know that the work done in the student to the system or from the system. Okay. Doing the same thing by storage. It's the same meaning, reversible power or maximum power. Okay, I get 5,056 kilowatt. So x1 and x2. Okay. So then next we have to calculate the actual one. P actual. So P actual is actually P reversible minus all the losses or minus all the exergy destroyed. Okay, so the exergy destroyed I have is M. Then this is exergy. Sorry, irreversibility. Okay, so S1, S2 plus the heat loss. Okay, so reversible power is 5056.03 minus natural rate 8 T0297 S1 minus S2 plus the heat loss. The heat loss we have is 300 kilowatt from here. Okay. So you will get 4285.58. Okay, the losses should be including the losses from the irreversibility and the heat loss. Okay, so we have the X1. Sorry, we answered ABC already. Now D, the second law of efficiency. Second law of efficiency, very direct forward now. P actual over P reversible. P actual is 5056 point, sorry. So we have 84.75%. Second law of efficiency. So the last one is to find the exergy destroyed. And we know that exergy destroyed is come from the irreversibility and the heat loss. Okay, or you can just take the reversible output minus the actual output. All the losses is counted as a exergy destroyed. So exergy destroyed is 770.5 45 kilowatt. Excuse me. Okay. Any problem on the exercise side? The question is similar to this lah. So normally they may have one or two questions asking about the theory, and then the last part should be the calculation. Mainly it's just about the steam engine. Okay, last one. Example 2.9. Steam enter a two-stage. This one is more complicated, two-stage. So it means that now you have two turbines. So you have to consider the turbine, one turbine and second turbine separately. Two-stage adiabatic turbine at 8 megapascal, 500 degrees Celsius. It expands in the first stage to a state of 2 megapascal and steam is reheated at constant pressure to a temperature of 500 degrees Celsius before it's routed to the second stage, where it exits at 30 kilopascal at a quality of 97. Quality of steam of 97% means that 97% of the exhaust or the gas is steam, and 3% will be in terms of water. So it's no longer superheated. Okay. The work output of the turbine is 5 megawatt. Assuming that the surrounding is to be 25 degrees Celsius, determine the reversible power output and the rate of electricity destroyed within this turbine. So the final answer, we need to find the reversible power output. So in other words, we need to measure the electricity change in the state 1 and then the electricity change in the state 2. And you combine them, you will have the reversible power. Okay, just do it separately. So first, maybe at state 1 or turbine 1. Maybe we calculate for turbine 1 first. So same thing, you have the state 1, state 2, and state 0. Then this is a turbine, so it's a flow system. So I need to find the entropy and enthalpy. V0 surrounding 100 kilopascal. If not stated, you can always use 100 kilopascal. So use the steam table. 8 megapascal, so it means that 80 bar. 80 bar, 100 degrees Celsius. Okay, so for this case, maybe we do it separately. We find the turbine one, the reversible power for turbine one, and exergy destroyed of turbine one. Okay, so let's say we want to find the reversible power for turbine one. Okay, so reversible power definitely. Do we need the mass for it? Total power is 5 megawatt. Okay, the mass for it we put it later. So we get in terms of kilo. We get in terms of exergy change first. S1 minus H2 minus D0 S1 minus S2. Kinetic energy and potential energy we don't have. Okay, so can directly get this. Okay, and then exergy destroyed. Should be equal to this D0 S1 S2. Okay, so this is all about the state one. I cannot find the mass flow rate first because I do not know what is the output at the state one. I only have the total output. So in other words, I have to find the overall reversible power. Okay, then I can get the mass flow rate. Now we go to the state two. Sorry, turbine two. So at turbine two, you also do the same thing. You have the state one, state two, and state zero. State one. So pressure. Okay, read carefully. The steam is then reheated at constant pressure to a temperature of 500 degrees Celsius. So it means that the temperature 500, but the pressure still remain at 2 megapascal, and this will be the input for state two. So E 2 megapascal, G1 500 degrees Celsius, and same thing, you need to find H1 and S1. And then the state 2, P2. Pressure will go up to 30 kilopascal as this. And temperature is not stated. Okay, we do not know the temperature when it exceeds, but we know that quality of the heat is 97. Okay. So we may need to use this to find the H. So H1, H2, and S2. Okay. Then the surrounding will be the same. State 0 will be the same as the turbine one. So let's find this first. 2 megapascal and 500. Okay. Then state 2, then I think we have to do together lah. So state 2, because of the quality is 97, so it means that it's still not yet 100% convert to steam. So we have to refer to the saturated table. Okay, and then I don't know the temperature, so I can refer to the pressure table. So the pressure is 30 kilopascal. 30 kilopascal refer to 0.3 bar. 0.3 bar. Okay, so 0.3 bar is over here. So what we need to do, you can see that we have the UF and UG, HF and HG. Okay, so it means that now 97 of the watt steam is HG, and 3% is HF. So in this case, I want to find H2. It means that 0.97 H is gas plus 0.03% H is free. Okay, which is water. Same thing for this, 0.97 Sg plus 0.03 Sf. Okay, so we find for Hg first. The kilopascal. So we take 2625 times 0.97 plus 289 times 0.03. I get 2554.92. Okay, and then for the entropy, same thing, 7.767, which is for gases. This one, times 0.97 plus 0.944 times 0.03. So I get 8.508. Okay, now we have all the entropy and enthalpy, then we can find the reversible work. Phi 1 minus phi 2. Sorry, psi, it's open flow. H1 minus H2 then S1 minus S2. S1 okay, and we also can get the exergy destroyed. Modulus 320.946 kilojoule per kg. Okay, so from here we get the exergy change for first turbine and second turbine, and also the exergy destroyed for first turbine and second turbine. So to get the reversible power, now what left over is actually the blast flow rate, and we know that the power output is 5 megawatt. Okay, so from this 5 megawatt, the actual should be equal to P reversible minus the exergy destroyed. But this is the total. So P reversible, total P reversible will be reversible for state 1 plus reversible for state 2. So 329 0.732 plus 1233.026 minus 963. Okay, and then remember you want to find the mass flow rate. And B actual is 5,000 kilowatt. Okay, so from here you can get the mass flow rate. So mass flow rate is 4.2659 kg per second. Okay, so we can get the reversible power. Just take the reversible power in terms of kilojoule per kg and then multiply with the mass flow rate. Y1 minus Y2 for state 1 plus Y1 minus Y2 for state 2. Okay, we should use psi. For state 2. Okay, we get the reversible power is 6.6667 megawatt. And then the next is the rate of exergy disruption. So same thing, exergy destroyed should be mass flow rate multiplied with the total exergy destroyed for state 1 and state 2. Okay. This is a bit long. So actually the concept is still the same, but now we do it separately. Turbine 1 and turbine 2. Okay, any question? Hello? Okay, maybe you need time to digest a bit. Okay, so I think that's all for today. And then we still have 1 week, week 14. Then that week we will use as a discussion for last passing question paper. And I won't make it compulsory. If you think that you are too busy or you want to make the revision at your own, it's up to you. Okay. So next week lecture is optional. If you choose don't want to attend, it's up to you. We will do a revision on the past year question. Okay, that's all. Thank you for your time, and then see you next week.
Thank you, sir.
Okay.